Hi, welcome back to this video lecture series on understanding natural language understanding. In this lecture, we're going to look at this NLU framework that me and my team are working on. So this is one way to perform natural language understanding. It's not the only one, but that's one way to do it. So first of all, what is really natural language understanding? It's different from natural language processing in the sense that NLP started as a way of really processing text in a very statistical manner, or even sometimes just by counting how many keywords appear in a document for topic modeling or for sentiment analysis. So NLU tries to really encode and decode meaning in a way that is very much cognitive inspired. So that's not this, as I said, there's not just one way to do this. And what we do is leveraging those pillars that we talked about in the previous lectures, like symbol grounding, intention awareness, and especially task decomposition, to create a framework that is attempting at least to look at a natural language and try to understand it rather than just process it. So the curse or blessing of NLU is really that everything is interrelated, and it's actually quite difficult because then it's really about human intelligence. How to encode and decode meaning is still a mystery that we haven't figured out yet. But then, given the right constraints and assumptions and specific domains and downstream tasks, it can be done reasonably well with relatively simple technology. It's also a question of how accurate do we want our systems to be. If you go work for a big tech company, then it's expected that you have 90+% accuracy. For a PhD, maybe 85. For a standard information retrieval assignment, maybe 80% accuracy is enough. So we're going to be looking at this suitcase model in this lecture. This is something that we have mentioned several times. It's called suitcase because sometimes when we talk about processing, we don't think of all the things that are inside this very complex word. And this is similar to when we talk to intelligence. Intelligence is also a suitcase word. There's so many things inside that we need to explain and sometimes build from scratch to truly be able to understand and build intelligence. So here is something similar to achieve a downstream task, like, for example, polarity detection. You could just train a statistical model that based on some probability, or even like a naive Bayes model that based on probabilities learned classifies text as positive or negative. But in this framework, we want to have a modular approach where we try to emulate all the cognitive processes that go on in our mind and sometimes very subconsciously to truly understand text. And this is good for several reasons, not just in terms of sometimes accuracy, but also it makes your framework much more interpretable, because then if you need to do any error analysis or ablation study, you can go back and see what is the output of every module. And based on this interpretability, you can also have enhanced explainability, because when you ask your model how it came up with such conclusions, it can go back and see which module generated the error or which module is responsible for each output. Having this modular approach also reduces hallucination, because you're kind of forcing your system to go through specific steps, reasoning steps. It's easier to have updates, because then if tomorrow there is a new algorithm, for example, for word sense disambiguation, I don't have to retrain the whole system, but I can just update this module. And because of this, it's also easier to do an evaluation of the system, doing an ablation study to see what's happening in the reasoning steps of my system. It's also more scalable, as we said, is more cognitive inspired and can be developed in parallel. So this is also important, and this is what we're doing in our research team. Different PhD students and postdocs are focusing on a different task, but then they can all be put back together to have a more holistic and comprehensive framework. This also increases the robustness of the system. So even if one module makes a mistake, sometimes it can be fixed by another module, and ultimately also how much we can rely on the system. So let's dive in and look at the different layers one by one. We'll start from the syntactics layer, which is a set of basic tasks that we do before diving into more complex tasks. So you can see this layer maybe as a sort of pre-processing layer, which is made of microtext normalization, sense boundary disambiguation, part-of-speech tagging, text chunking, and lemmatization. So just to clarify that each of these modules, it's that they are not a must use every time. So microtext is a good example of the fact that sometimes you may not need it. If you're working with formal texts, then you don't need a module for microtext normalization. But if you're working with social media text, then you probably need it because this allows you to convert informal text like phonetic expressions, acronyms, emoticons, emojis, and so on into more formal text. Why? Because as we mentioned, text is just a representation for a sound that is then connected to meaning. And in some cases, when you're looking at English slang or even some other languages, like maybe Singlish, they don't have a specific canonical structure for every word, then the best thing to do in that case is to have a system that can convert a specific spelling permutation in a more canonical form that can be recognized or stored in a dictionary or in an embedding model. Macrotext also is about, for example, converting British to American English, because then you don't want to have duplicates like color and color in your dictionary, and also it can go as far as semantic similarities. So in this video lectures, I'm not going to go too much into details, but if you are very interested in any of these modules, you can go and read more in the book. Each of these modules actually can be a PhD topic. For example, this was a PhD topic of my PhD student Ranjan, that has been looking at all these data sets and tasks that need microtext normalization to have a better accuracy on the final downstream tasks. So here you can find all the different tasks that can benefit from microtext normalization, including all the many data sets that are, many of them publicly available, and that you can also use for your assignment. Okay, next we have SBD, sentence boundary disambiguation. This can seem very trivial, but actually it's not, because in English we use dot to finish a sentence, but in many cases the dot doesn't equal the finish of the end of the sentence. So it's also important, especially because many classifiers are sentence level, to have a system that can really define the boundaries between sentences. So this is something that has been explored a lot in the past, and in the book you can find more information about past algorithms and widely used corpora for SBD. Post tagging or part-of-speech tagging is also very important for languages like English that are relatively simple, in a sense that the same word can be used for different purposes and can have different meanings depending on the part of speech that they represent, whether they are a noun, an adjective, a verb, and so on. And this is particularly important for sentiment analysis because the same word like fine, for example, can be positive as an adjective, but negative as a noun. And again, on the book, you can find a lot of algorithms that tackle the problem of post tagging and a lot of corpora that are used for the evaluation of post tagging from different points of view, from feature engineering, deep learning, semi-supervised, and some other more heuristic approaches. Text chunking is also a lexical subtasks that is important to divide the text in specific chunks. And this can be important for sentences that are a bit complex, those that have a lot of parts, a lot of chunks that are nested into each other that can be confusing sometimes for a classifier. And again, in the book, you find a lot of resources and data sets that can be used for text chunking. Last but not least, we have lemmatization, which is also a very important NLP task. And this can really much be very good for removing, for example, duplicates in your dictionary. So, for example, if you have a concept level dictionary that has multi-word expressions like this, eat burger, you don't want to save so many times all the inflections, the possible inflections of this concept, because they all represent the same thing, right? You want to do some pre-processing like stop word removal, removal of ing form, and so on, so that you save just the most canonical, most representative version. Then, of course, the same kind of pre-processing that you do, you will have to do also on text later on. Another way of doing this kind of pre-processing is instead to use stemming. Stemming, instead of looking for the lemmas or root words, is just cutting off the suffixes like ing form or ed, which normally is a smart thing to do because it's also much easier than lemmatization. But it's not always the case, because in English, you have a lot of words that when you apply stemming, actually you get something that is completely different. You have some examples here. Cater become cat, fasting become fast, dental becomes dent, and so on. Caring becomes car. So you can use stemming sometimes. For example, in your assignment, you could use Porter's algorithms for applying stemming. And so it really much depends on the downstream task and the data that you're using. What's good about lemmatization, although it's more complex than stemming, is that it preserves the part of speech tagging. If tagging is important for your downstream tasks, then you definitely need to use lemmatization. As you see in this example, all these in the case of stemming, all these inflections of the word Democrat get processed as Democrat, which is good if you're just doing topic modeling. But if you needed the post-tag information, then it's better to use lemmatization. And this is true for many other tasks where you need maybe a more fine-grained analysis, where you need to know the difference between seasoning and season, or maybe the difference between developing versus developed country, which would otherwise be normalized to just developed, fasting, fasten, and so on. So once again, in the book, you find a lot of information about possible algorithms and widely used corpora for lemmatization, and all the tasks that can benefit from lemmatization. Okay, that concludes the syntactic layer. we can go on into the semantics layer, which is slightly more interesting because we start looking at some tasks that are more useful to really understand text. So we have word sense disambiguation, name entity recognition, concept extraction, and upper resolution, and subjectivity detection. So actually, when we talk about semantics in different disciplines, they can mean different things. Like if you talk about linguistics or NLP or even philosophy, semantics can mean different things. In our case, we're just looking at how these can translate then into useful concepts that then can be later on used by the pragmatic layer. And here you also have some examples of downstream tasks that use word sense disambiguation, name entity recognition, concept extraction, and so on in different ways. Of course, this is not a comprehensive list. It depends, again, on what kind of task and what kind of data you are dealing with. So this is just an example. So in the case of word sense disambiguation, this is again very important, especially if you're working with languages like English that tend to reuse the same word for different meanings in different contexts. So this is something that even we understand better given a specific context. And this can be extremely useful again for polarity detection. As you can see, the same word in different contexts can have opposite polarity. And there are many different methods that we can use here. In the past, we used a lot of knowledge base or sense disambiguation algorithms. Now it's more about statistical WSD. And once again, you can find different resources and data sets that you can use to train and test your WSD algorithms. Name entity recognition is particularly important for concept extraction because then you can have those multi-word expressions like names of people or names of companies that need to be recognized in text. And here in one example of this is the word kiwi that can mean different things in different contexts. Kiwi can be the fruit, can be the animal, or can be someone from New Zealand. But kiwi is a simple example of a one-word name entity. In most cases, you have a very complex and nested name entities like West African crocodile. And so people had to come up with different annotation schemes to be able to catch all these name entities. And in the book, you have more details about different data sets and different approaches to name entity recognition. This is still a very much research topic. I still have some PhD students focusing specifically only on NER, and there are different approaches that you can take, even hybrid approaches where you're using a statistical model together with a graph solution to represent and detect name entities. So again, in the book, you can find more information about this representative application of NER, resources, and data sets. But this will be very much specific to the domain, the kinds of name entities that you're working with. Concept extraction is about extracting concepts or multi-word expressions from text. So here again, you can use a hybrid approach where you take on a statistical methodology, but also you can have a graph to represent different multi-word expressions, but also to represent words. So here in this example, you can have some symbol grounding algorithm that explains what's the meaning of trust. And then on top of this, you can have all the possible inflections in English that are related to trust, both the positive ones like entrusted and the negative one like distrustful, for example. So here you also may want to apply the things that we mentioned earlier, like lemmatization, removal of stop words, and other kind of pre-processing tasks that we mentioned earlier. So this can be as simple as calling a function by NLTK to remove stop words, but normally it's better if you have your own list of stop words based on your own data rather than using someone else's stop words. And another thing that we normally do is to do case folding to extract concepts, but sometimes this can lead to some errors, because in some cases, looking at the case of words like COD versus COD, WHO versus WHO, or Polish versus Polish can be a problem. So again, there's no universal solution to the pre-processing that you need to do for concept extraction. It very much depends on the kinds of concepts that you're dealing with, the data, the downstream task. But nonetheless, on the book, you find a lot of data sets and resources for concept extraction. So you're welcome to take a look. We also have our own concept extraction tool. It's called Centric Parser, and that's also available in our download section. Next, we have anaphora resolution. This is something that we already discussed earlier when we were talking about self-attention. It's about resolving pronouns. So if you have a pronoun like it in a sentence, what does this it refer to? It, them, and so on. So this has been a very complex task that in computational linguistics has been explored for many years. And on the book, you find more details about this, different data sets, different resources. Again, CenticNet is also looking at this, and all the downstream tasks, some of the downstream tasks that can benefit from anaphora resolution. So this, again, is not a must, but if you have a lot of pronouns in the data that you need to process, then you definitely need a tool for anaphora resolution. Last but not least, we have subjectivity detection that can be really useful in the case in downstream tasks like polarity detection, but also in some other downstream tasks, because it pre-classifies text into different categories. It can be objective text that is neutral, that doesn't contain any opinion, or it can be a subjective text that later on needs to be classified as positive or negative, or even ambivalent when you have opposite opinions in the same sentence. And so this has been an important pre-processing tool especially back then when we had classifiers like SVM that work best on two classes. So subjectivity detection is really powerful, because instead of classifying, for example, text as positive versus negative versus neutral, you first classify text as either objective and subjective, and then only those that are subjective, you pass it to a polarity classifier that does a binary classification into positive versus negative. So here you have a lot of data set and resources in different languages, English, Spanish, and so on, and some useful knowledge bases that you can use for subjectivity detection, including CenticNet. And more resources and more data sets are again in the book, and you also see what kind of algorithms have been used in the past to do this kind of binary classification. Okay, that concludes the semantics layer. And finally, we go to maybe the most exciting one, is the pragmatics layer, where we have much more complex natural language tasks to tackle. The first will be metaphor understanding, which has been the holy grail for many years, because it was very difficult to to develop. Then we have sarcasm detection, also very complex because even humans sometimes cannot detect sarcasm. Personality, aspect extraction, and polarity detection is the downstream task that we pick. Here, once again, you have some of the tasks that benefit most from the subtasks of the pragmatics layer, but again, it's not a comprehensive list. A metaphor, again, is a very complex process because it's actually made of two subtasks itself. First, you have to detect the metaphor in text, and then you have to understand it. And when I mean, what I mean by understanding is to be able to really kind of convert or translate into plain English what the metaphor stands for. And so this is something that for many years has been very difficult to achieve. And you can find more information in the book about the different data sets and resources that have been used. In our group, we have been working a lot on this. Recently, we also have tools, free tools that you can use. MetaPro is one of these. And then it's a very important task that can really change the accuracy of a downstream task like polarity detection, for example. Sarcasm, as I mentioned, is a difficult task that requires a lot of understanding of what's happening in the sentence, and many different kinds of learning have been explored. For example, multitask learning to understand sarcasm together with polarity detection. And in the book, you can find different data sets about this, especially a lot of multimodal data sets for sarcasm detection. So, and the multimodality of sarcasm is really interesting because you have cases like this here on the right, where you have a picture that by itself is not sarcastic, and also a text like this, what a wonderful weather, that by itself is not sarcastic. But when you put these two together, that's when it becomes sarcastic. So this extra dimension of sarcasm in multimodal sarcasm detection is very interesting and still a matter of research in different contexts, different domains, and also for different downstream tasks. In fact, sarcasm can be very useful to detect the personality of a user. And personality recognition can be very important in the context of intention awareness or personalization. So this is very much based on psychology studies and models that have been used in psychology for many years, for in domains like mental health application. The Big Five or Ocean is definitely one of the most famous ones, but recently there have been others that have become more and more popular, like MBTI. So most psychologists don't recognize MBTI as an official model, but still it has its own advantages. So for once, it's very modular. So you can just apply a binary classifier, for example, to choose between extraversion and introversion, and then another classifier for sensing versus intuition. And once you have all these together, once you put all these four classifiers together, you get one of those MBTI labels like INTJ and so on. So here, you also, in the book, you find information on how these data sets are built, both for Ocean and for MBTI. So you can choose which one suits better your data and downstream tasks. And in the book, you find different data sets that use one of these two models and different downstream tasks that benefit most from personality recognition, specifically recommendation systems and social network analysis. Aspect extraction is an extremely important task to do fine-grained sentiment analysis. If you take a sentence like this, for example, I love iPhone's touchscreen, but the battery life is so short, and if I try to classify this piece of text as positive or negative, I probably get something neutral because I get something positive, something negative. What do I do with these? If I do a mean, then I get neutral. But actually what I should do is to extract aspects first, in this case, touch screen and battery, and then assign a polarity to each of these. So this can be very powerful to better understand what users like or dislike about a different product or service, and also very useful for comparative evaluation. So let's say I have two digital cameras. If I how to compare these two, I can just calculate the polarity and see which ones have a higher polarity. But the best thing to do is to deconstruct the digital camera into the specific aspects that represent best the camera, and then calculate a polarity over thousands of reviews for each of these two, so that I can better compare them in terms of what are their each own strengths and weaknesses. So this is a very important task that today is still very much research on. And in the book, you find information about different ways, annotation schemes, different data sets, and also different subtasks, because then I just talk about aspects in general, but it's also about detecting different aspect terms versus aspect categories and the polarity of each of these. In the book, you also find different resources for aspect extraction like Probase and PrimeNet also, that we'll talk about in the next lecture, and a lot of data sets for evaluation, and also the problem of implicit aspects that are mentioned only implicitly, and all the different subtasks of aspect extraction, like aspect-based sentiment analysis, aspect category sentiment analysis, and so on. So that really much concludes the suitcase model. The last bit is the downstream task. That could be any task. And here we put polarity detection because it's one of the things that we do. So polarity detection, again, is just, simply put, is just a binary classification of text into positive versus negative. So we could, again, just train a classifier to do this. But if we have that task decomposition approach, then we definitely have a more interpretable output, and that is more understandable, more prone to explainability as well. And here in the book, you find some technical trends and data set and resources like CentiNet and many others for polarity detection, which can itself be a subtask for more advanced tasks like human-robot interaction, recommender system, and also finance. Polarity detection and sentiment analysis can be very useful for financial prediction, for example. Okay, that's all. That concludes lecture number 4, which was about the suitcase model. I hope everything is clear. If you have comments or questions, don't hesitate to ask. And I'll see you next time for the final lecture on neurosymbolic AI. Ciao.